In this example, we are asked to compute the flux of this vector field across a surface, where the surface is the portion of the paraboloid which lies above this square, 0, 1 in the xy plane. So let's try to figure out exactly how this is going to work. So first of all, let's remember what the formula for flux is. The flux of a vector field is defined to be the double integral over this surface of f dotted with ds, where this ds is the vector, it's the vector differential, right, which is considered to be so another way to write this, in other words, is f dotted with the normal vector field, or the Gauss map, ds, where this is just now a regular surface integral. But let's remember a couple of things here. The n in this situation is equal to, so if there's a parametrization of our surface, which we'll think about in a minute here, probably there will be, this is the graph of a function, so it'll be pretty easy to write down a parametrization. But if there's a parametrization, then n is equal to the normal vector with respect to the parametrization divided by its length, right? And moreover, what? This vector nu is just the cross product of r sub u cross r sub v. All right? Moreover, again, so another thing that we know here is that the surface area element, when there is a parametrization, is given by the length of the same vector nu times dA, where this becomes the area element in the parameter domain D. And so after all of this, what can we do? We can say, oh, well, n is this, ds is this. If we multiply this together, n times ds, this is what ds with a hat is, by the way, then this is just nu over length of nu times length of nu dA. And so in terms of our parameter domain, remember we have a smooth surface always here, so this is never 0. And our ds, our vector term ds here, is just the normal vector nu times dA in the parameter domain. All right, and so the flux, when we want to compute the flux over a parametrized surface, we can just use the parameter domain to do that work in. And this right here, this nice little square, is our parameter domain for this function. Okay, and this is the key part of the parametrization right over here. So let's write this all out. We are going to make this identification then, right? So we are going to say, all right, our D in the xy plane is 0, 1 crossed with 0, 1. Let's just for the sake of all this, let's get the u's and v's in there. So x is equal to u, y is equal to v, z is then equal to 4 minus u squared minus v squared. Okay, and this is our r, right? So this is our r, and we can use this then to compute our area element ds. So we need then I'll write everything out again. R is u v 4 minus u squared minus v squared. R sub u is the partial derivative of this with respect to the u variable, so it's 1, 0 minus 2u. R sub v is 0, 1 minus 2v. All right, and then we need to compute the vector nu. The nu is the cross product, right? So nu is going to be 2u, it's going to be 2v, and then finally 1. So there's the vector nu. The other thing we need to do is we need to get our vector field f in terms of u and v. Right? So I'm going to rewrite this down here. So our vector field f is going to be, let's go back, it's xy, yz, xz. So xy, yz, xz. We need to get the u and the v parameters into this vector field. And so when we do so, the first term is just uv. The second term is going to be what? V times all of this, right? So 4v minus u squared v minus v cubed. And then the third component is going to be 4u minus u cubed minus uv squared, right? uv squared. And finally, we're going to integrate this up, right? So let's just write down the integral that we're going to compute. The flux of f across S. All right, we're going to compute this as the double integral over our nice rectangular domain D of f dotted with new dA. All right, and so that means we need to take the dot product of these two vector functions, and this will be then the double integral over d of, just multiply all this out, right? So this is 2u squared v plus, this is going to be 8v squared minus 2u squared v squared minus 2v to the fourth, and then plus 4u minus u cubed minus uv squared, all dA. This is what we need to integrate. So this is our integral. All right. So at this point, I would say pause. Make sure you make sure that this whole setup made sense to you, and then just compute this integral. And I'm going to work this out, but take a pause. Make sure you can do this, and I'll see you in a minute. So this is going to be integral 0 to 1, 0 to 1. Let's combine like terms now. So we have 2uv squared minus uv squared. That's u squared. No, those aren't the same. So none of this combines, does it? All of these terms are different, so we just have to integrate. Okay. So 2u squared v plus 8v squared minus, this is very symmetric, so we can do either integral first. The bounds are the same, so I'll do the u integral first. So integral 0 to 1. By the way, when you integrate, we're going to then plug in the bounds 0 and 1. So this becomes 2/3 v plus, that's just 8v squared, minus, this is another 2/3 v squared. And this is minus 2v to the fourth. This is plus 2u minus 1/4, not 2u, it's just 2. All right, 2 minus 1/4. And then finally, minus a half v squared, all dv. And so we do this integral. Same deal here, right? So this one's going to be 1/2. So this is 1/3 plus 8/3 minus 1/3, no, 2/9, minus 2/9 minus 2/5 plus 2 minus 1/4 minus 1/6. All right, and all this has to get added up now, and then we'll be done. So this part is 3, 4, 5. All right, and then any reduction here? Not really. So then we have, what's left after all this? Let's just do these in groups. So this one's going to be minus 10 plus 18, so 28/45, minus this one's going to be 6 plus 4, so 10/24. And after all this is going to be 5. So this all works out to be 712 over 1080. And then this combines one more time, so 5 times 1080 is equal to 5400 minus 712 over 1080, and our final answer here is just going to be this difference, so that's going to be 4688 over 1080. This will reduce, but I've had enough of it, so we're going to leave it like this. So this is the answer to the flux of this vector field across this surface.